In the sixth lab this semester, we investigated the question, let's suppose we have a region with a well-defined boundary, and we'll assume that there are no charges present anywhere nearby. So if the electric field is going to be zero everywhere outside this region, is there some solution to the question, what is the electric field inside the region, other than the electric field is zero everywhere inside the region? And we found that the answer to that question was yes. The solution to that question, to the electric field inside the region, is the electric field could be some type of wave solution. So let's apply Faraday's law to a wave. So Faraday's law, even though we haven't formally worked with it yet in this course, a lot of the techniques we use when we work with Ampere's law will apply to Faraday's law as well. So we say around a closed loop, instead of talking magnetic field, we're talking electric field, but still in both cases we're working with a vector field. So the usefulness of you want to often walk in the same direction or perpendicular to your vector field, a lot of those techniques will still apply. So around a closed loop, E times delta L times cosine theta equals negative rate of change of magnetic flux. So we're going to apply Faraday's law to an electric field wave. So here I have E plotted versus position on the x-axis. When I am working through this exercise, I'm going to be a bit hand wavy with some of the steps I do. What I'm doing is not a formal proof, but it is strongly suggestive of a really interesting result. So we're applying Faraday's law. We need to walk around a closed loop. Let's be creative with the closed loop we choose. So let us choose a closed loop that is, we'll walk upward here. And let's say we walk in total a height equal to h. So the total height we walk is going to be a height of h. And then we will turn and walk to the right. So now we are walking perpendicular to the direction of the electric field. Let's suppose we walk a short distance to the right. I'll call this short distance delta x. So the distance I walk to the right is just going to be delta x. Then I will turn and walk downward. So I will walk down, and then I walk down some more. So now I'm walking down a height h, and then I'm going to walk to the left a distance delta x and come back to my starting point. So I walk a distance delta x to the left, and I end up back at my starting point. So this is the closed loop that I'm traveling. I'll begin down here and walk in a rectangle in a clockwise direction, a height delta h, a width delta x. So let us notice that when I'm walking upward, the electric field is stronger than when I'm walking downward. In both cases, the electric field is pointing upward, but on the path up, the electric field is a bit stronger. So let's say on the path up, the electric field is equal to E plus delta E. And on the path down, the electric field is just equal to E. And in both cases, it's pointing up. So when I'm walking upward, the electric field is in the same direction that I'm walking, and it's a bit stronger by that much. When I'm walking down, the electric field will point the opposite direction, and it will only have that much strength. So the strength of the electric field I could say, okay, here's the path down. So I will say this is the electric field E, and the remainder, the excess electric field when walking on the path upward, will be E plus delta E. So this will just be a delta E more. Okay, now we have everything we want to apply and work out the left-hand side of Faraday's law. So around my closed loop, I will begin right here and walk in a clockwise direction. So the first part of my journey, I'm walking upward. I'm walking in the same direction as the electric field. So on the path upward, I would have the electric field has strength E plus delta E. This is my E. My L, the distance I walk, is a height H, the distance I walk. And then I have cosine of 0 because I'm walking in the same direction as the electric field. Then I will turn and start walking to the right. When I walk to the right, I walk perpendicular to the electric field, so it does not matter what I have for E and delta L, because I have cosine of 90 degrees, which is just 0 anyway. Then I will turn and walk downward. So on the path downward, I am walking in a region where the electric field has a strength E, only a strength E now. So I will have electric field E. The distance I walk again is H. And now the electric field points up, but the direction I'm walking is down. Those two directions are perfectly opposite. So I have cosine of 180. And again, I am turning and walking to the left now. The electric field points upward. The direction I'm walking is to the left. Those are again perpendicular, so I get, it doesn't matter because I have cosine of 90. So the path when I'm walking to the left and the path when I'm walking to the right are both going to be 0, so it really doesn't matter what terms I have for E delta L here. So the left side of Faraday's law ends up becoming E plus delta E times H. Cosine of 0 is just equal to 1. Cosine of 180 is equal to -1. Then so this plus 0 minus E times H plus 0. So the path up, the path walking to the right, the path down, the path walking to the left. And all of these will add up to the rate of change of magnetic flux, delta phi b delta t. In the next step, I'm going to continue looking at what happens to the left side of Faraday's law. So I'll just factor the H in here. So I get EH plus delta EH minus EH is equal to rate of change of magnetic flux. So negative delta phi b delta t. And then I notice I have plus EH over here, minus EH over here. So I get then delta E times H is equal to negative rate of change of magnetic flux. Okay, we solved the left-hand side of Faraday's law for this scenario. Let's focus on the right-hand side of Faraday's law. So the right-hand side of Faraday's law, where I have my, I'm going to look specifically at the delta phi b delta t. What's happening with this term? Well, What is magnetic flux? In this problem, magnetic flux is going to be B times A. A is the area of the path I walk around. B is the strength of the magnetic field. So this is going to be delta BA delta T. Now, in this problem, A is going to be, again, the path I walk around. So A is the area of my path. So in this case, area would be just width times height. So area would be equal to h times delta x. Now, this area is also going to be constant because the area isn't really affected by other things. It is something I choose, and I choose a certain path. The size of that path is not changing throughout this problem. So I could then factor the A outside, and I could then write delta phi B, delta T is equal to delta B delta T times area, and area is H delta X. So when I take this term and I plug it into Faraday's law, what I find is delta E times H is equal to negative delta B delta T times H delta X. And at this point, I notice I have H on both sides, so I'm going to cancel those out. And I'm going to bring the delta X to the other side. So what I end up with when I apply Faraday's law to an electric field wave solution is delta E delta X is equal to negative delta B delta T. So what we're going to do now is we are going to perform a similar analysis to the magnetic wave using Ampere's law. We're going to get a different solution to this problem, and then we're going to combine these two solutions. So here we have Ampere's law, and we're going to apply Ampere's law to a traveling magnetic wave. Now with Ampere's law, one significant difference is on the right-hand side, we have both an enclosed current, which is a traditional current, charges moving from point A to point B, and we have a displacement current. In this example, we are assuming everything is occurring in vacuum. In other words, there are no sources of electric or magnetic field present. So if there are no sources present, that means there are no charges. And if there are no charges, that means there are no traditional currents, charges moving around. So I enclosed, we are going to assume is equal to 0 because there are no charges present. Now, in a previous PowerPoint slide, we said that the displacement current, I displacement, is equal to epsilon naught times the rate of change of electric flux, so delta phi E delta T. And when I plug 0 in for the enclosed current and the rate of change of electric flux for the displacement current, in this particular scenario where there are no charges present, then Ampere's law becomes around a closed loop. B delta L cos theta is equal to mu naught times 0 plus epsilon naught rate of change of electric flux with respect to time. So we're going to perform a very similar analysis to what we did in the previous with Faraday's law. So I'm going to choose a path to walk around. This time I'm going to choose a counterclockwise path to walk around. I don't really want to get into the details, they're very subtle of why we're doing this, but it has to do with the right-hand rule, but I'll just say for the purpose of this course, don't really worry about that. So the path I'm going to walk, I will begin right over here, and I'm going to walk to the right a distance delta x, just like before. And then I will walk upwards a distance h in total. Then I will turn and walk to the left a distance delta x again. So here is a height h. And then I'm going to turn and walk downward. Now, if you notice on how I chose to draw this path, when I'm walking upward, the strength of the magnetic field is B. When I'm walking downward, the strength of the magnetic field is B plus delta B. So in a way, we have the reverse situation. When we're walking upward, we have a smaller magnetic field. When we're walking downward, we'll have a slightly bigger magnetic field. So I am going to, again, look at every term on the left-hand side of Ampere's law. So the B delta L cosine theta, I have to consider all four paths. So the path upward, I would have B times H times cosine of 0. Then for the path when I'm walking to the left, I would have B times delta X times cosine of 90. Cosine of 90 is just equal to 0, so it doesn't matter what is over here because it will be multiplied by 0 anyway. On the path downward, I have a stronger magnetic field. So on the path downward, I will have B plus delta B times H. And this time I'm walking down, but the magnetic field points upward. So I have cosine of 180. And then I walk to the right to get back to my starting point. But again, the magnetic field points up. I'm walking to the right, so I have cosine of 90 again. So it doesn't matter what term is here and here because cosine of 90 is just equal to 0 anyway. Cosine of 0 is equal to the number 1. Cosine of 180 is equal to the number -1. So what I get is B times H times 1 minus B times H minus delta B times H. So this term right here is the left side of Faraday's law as I walk, or sorry, the left side of Ampere's law as I walk around my closed loop. The term when I'm walking upward has a weaker magnetic field. The term when I'm walking downward has a slightly stronger magnetic field. I factor the H in, that gives me these terms right here. Now, I look again, I see a BH and a minus BH, so they cancel. And what I'm left with on the left-hand side is negative delta B times H. Now I'm going to analyze the right-hand side of Ampere's law. So I have this being equal to mu naught epsilon naught times the rate of change of electric flux with respect to time. Now, just like before, this term, rate of change of electric flux with respect to time, delta phi E, delta T. I could write this as delta EA, delta T. And the area here is constant. The area is just the area of this loop that I am walking around. So the area would be this entire area right here. So this area is delta X for a width and H for a height. So I could write this as being equal to delta E, delta T, times area. Area is constant, and area is h times delta x. So the area became this term here. And so I could just plug this term in over there. And when I apply that to Ampere's law, I get negative delta B times H on the left side equals mu naught epsilon naught times delta E over delta T times H delta X. Now at this point, I'm done with everything, all of the physics of this problem. I'm just going to rearrange the algebra a little bit. So I notice H is on both sides, so I could cancel those. I'm going to bring delta X over to the other side. And when I do that, I will have my form of Ampere's law that I want. Negative delta B delta X is equal to mu naught epsilon naught delta E over delta T. So this is the version of Ampere's law that I'm going to work with now. So what we found is when we considered walking in a closed loop around an electric field wave, from Faraday's law, we discovered delta E over delta X is equal to negative delta B over delta T. And when these deltas become really small and become infinitesimally small, I could write this equation becomes the partial derivative of E with respect to X is equal to the negative partial derivative of the magnetic field with respect to time. Now, in this course, this is a calculus-based course, so you won't actually need to solve any integrals or derivatives. But you won't see anything like this on an exam. But I think there is value in actually showing and demonstrating the derivation here. So I'm going to propose that the solution to this equation, so I'll say the proposed solution is E is equal to E naught sine kx minus omega t, and B, the magnetic field, is equal to B naught sine kx minus omega t. So this is just the proposed solution. It is possible to demonstrate and derive the solution, but I'm just going to propose the solution, and then we could check it and see what are the consequences of the solution. Now here, E naught and B naught are the amplitude of the wave. So E naught and B naught are the amplitude, which is basically the max value of the wave. And then the wave, sometimes the wave will be at its maximum value. That's when the sine of this angle is going to be 1. Sometimes the wave is going to be less than the max value. And during those times, sine of this kx minus omega t is going to be some number less than 1. So let's take the partial derivative with respect to x, the partial derivative with respect to t, and see what we get. So what I am doing is I am taking what we found with Faraday's law, dE dx is equal to negative dB dt. Now in this equation, I am not working with full derivatives, I am working with partial derivatives. A full derivative would be written as dE dx. A partial derivative is written as a cursive dE dx, like this. So I'm considering the partial derivatives here. So the partial derivative of E with respect to x is going to be the partial derivative of this entire thing the amplitude or the max value of the wave. The max value is constant because you only have one maximum value, sine kx minus omega t. So let's see, E naught is constant, so that comes outside. The derivative of sine is cosine, so we'll have cosine times the kx minus omega t, whatever's on the inside, times the derivative of the inside with respect to x. The derivative of kx minus omega t with respect to x would be just k. So d dx is going to be E naught times k cosine kx minus omega t. What about the derivative of b with respect to time? Okay, we could figure that out too. So the derivative dB d partial of magnetic field with respect to time, I will get, okay, partial with respect to time of b naught sine kx minus omega t. So b naught, again, your maximum value is constant, so that could come out front. The derivative of sine is cosine times whatever's on the inside. I'm basically applying the chain rule, kx minus omega t, times the derivative of the argument here. So the derivative of this stuff with respect to t would be negative omega. So then I get the dB dt is equal to negative b naught omega cosine kx minus omega t. And I previously found that the derivative partial e with respect to x is equal to E naught k cosine kx minus omega t. So let's take this result, plug it in up there. Let's take this result, plug it in there. And when we do that, what I find is, okay, dE dx is all that stuff down there. So that would be E naught k cosine kx minus omega t is equal to negative dB dt is all this stuff here. I have another negative there, so I'll do parentheses, this negative b naught omega cosine kx minus omega t, and then close that parenthesis. And now, okay, negative, negative cancel, so I get E naught times k, the magnitude of the electric field, cosine kx minus omega t is equal to b naught omega cosine kx minus omega t. So now I notice cosine kx minus omega t is common to both sides, so I could cancel these two terms. And if I rearrange this, I could write E naught over B naught is equal to omega over K. So E naught over B naught is equal to omega over K. Okay, so from chapter 11-15, if you have a wave and that wave is going to be moving, and if waves move, they're going to move at some speed. Omega over K is the speed of the wave that is moving. So omega over K is the speed of the wave. Also, if you think to the problem we talked about in the magnetism chapter, where we went through the example of how the electron was discovered. We discovered that for the electron to come in with the speed v, if the electron is to move through the undeflected path, the electron speed was given by E over B. Here again, we have an E over B, and that's equal to something like a speed. Now this is the speed of a wave. This is well understood physics. We did not cover this in 121 or 122, but this would be material from chapter 11-15. For that being the speed of the wave. So we found a relationship between the speed at which this wave moves and the strength of the electric and magnetic fields when they're at their maximum. We are going to take our proposed solution and apply our proposed solution to Ampere's law in a very analogous manner. In the limit where these deltas become infinitesimally small, the delta B over delta X will become a partial derivative of magnetic field with respect to X. And again, a full derivative is just symbolized by a lowercase d. A partial derivative is symbolized by a cursive d. So what I have on the left-hand side of Ampere's law is the negative partial derivative of magnetic field with respect to position is equal to mu naught epsilon naught, the two fundamental constants of nature, partial derivative of electric field with respect to time. So what is this partial of B with respect to X? We could find that. So partial with respect to X of this term here, I have B naught sine kx minus omega t. So let's see, B naught is the amplitude or the maximum value of the magnetic field. That is a constant in what we're talking about here. So I have B naught will come out front because it's constant. I am taking a chain rule of B. So sine becomes cosine. Then I leave the inside alone for the moment. Then I take the derivative of the inside with respect to x. That derivative will become k. So then I get equal B naught k cosine kx minus omega t. So this is partial of B with respect to position. Now I'm going to do something very similar for the electric field with respect to time. So I get partial of E with respect to time is going to be partial with respect to time of E naught, the amplitude of the electric field, which is again going to be a constant, sine kx minus omega t. So E naught will come out front. Then sine becomes cosine. We just leave the inside alone for the moment. Then the derivative of the inside with respect to time will become negative omega. So I get the partial of the electric field with respect to time is negative E naught omega cosine kx minus omega t. The negative omega, here's the negative, there's the omega. So what I'm going to do is I'm going to take this result for partial of E with respect to time, plug it in there, partial of B with respect to position, I'll plug it in up there, and we'll see what Ampere's law gives us. So when I plug these values in, I find that negative dB dx, so that'd be negative B naught k cosine kx minus omega t equals mu naught epsilon naught dE dt is that term there. So I have negative E naught omega cosine kx minus omega t. Okay, so at this point, I am going to perform some arithmetic on this. I have omega naught epsilon naught times negative E naught omega naught cosine of stuff. So this negative I could just put out front. And now very explicitly, I have negatives on both sides, so I could cancel the negative terms. So I could write this line as B naught k cosine kx minus omega t equals mu naught epsilon naught E naught omega cosine kx minus omega t. So let's see, we have cosine on both sides, so the cosine terms could cancel each other out. And I'm going to choose to arrange this in a specific way. So I will choose to bring mu naught epsilon naught to the other side, and I'll bring b naught times k to that side. So what I get is 1 over mu naught epsilon naught is equal to E naught omega over B naught times K. Okay, why was I inspired to write it in this manner? The reason for that is, if I look over here, the speed of the wave is omega over K, and we said that the speed of the wave is also given as E naught over B naught. So really, I could write this as 1 over mu naught epsilon naught is equal to omega over K squared. So I could write the speed of the wave is equal to omega over K is equal to 1 over square root epsilon naught times mu naught.